It's reasonable to ask, why hurricanes? What is it about the Earth atmosphere system that leads to the formation of such massive and energetic storms? Well, virtually every storm on Earth ultimately comes from the energy coming from the sun. So when we think about why hurricanes, we must start with the sun, its energy, and how that energy is redistributed once it hits the ground and moves around in our atmosphere. We get 100%, almost 100% of our energy from the sun. And as the sun's energy enters our atmosphere, some of it is going to be absorbed by the stratosphere. About 19% on average is absorbed by our atmosphere of the 100%. And then another 6% is just going to hit things in the atmosphere, particles in the atmosphere, bugs, planes, whatever, and be reflected back out to space. Another large percentage, about 20%, is going to hit a cloud on the way in and also be reflected and not make it to the ground. And then another 4% makes it all the way to the Earth's surface, strikes something shiny like water at an angle, and is reflected back out to space. So we wind up then with a total of about 30% of the energy either being reflected and 19% of it being absorbed in our atmosphere and not available to heat the ground. Of the total, about half actually makes it to the ground and is absorbed by the surface. Everything with a temperature is going to emit radiation. The ground, warming because of the incoming solar radiation, then warms the surface of the Earth, which in turn then is going to radiate energy back into the sky. But this energy is now at a different wavelength. This coming in from the sun we call shortwave radiation, solar radiation. Once the ground is warmed, it's now going to emit radiation back into the atmosphere as long-wave radiation. So if we're keeping track, then we're kind of up 51 units here in heavy trading in terms of warming the Earth's surface. And the atmosphere is up 19 units, and 30% has been returned to space. Now we're going to exchange this energy between the ground and the atmosphere. So some 7 units makes it through convection, sensible heat, the heat you can feel, move from the ground into the atmosphere through convection. A larger portion, some 23%, makes it from the ground into the atmosphere through evaporation. And you all can appreciate evaporation when you walk out of the shower and you're feeling chilled by the wind. It's that cooling effect, the energy it takes to evaporate water. We call this latent heat, latent meaning hidden. The heat is hidden because it takes energy to evaporate it. That water vapor that it becomes is going to be moved somewhere else where it's going to condense, and the heat gets released then in the atmosphere where clouds form. We'll come back and talk about that in a moment. Then we have the infrared part, the energy of the ground. The ground has been warmed. It's now radiating at a long wavelength, at about 10 microns of wavelength, into the atmosphere. And some 117 units. Now that's surprising, I'm sure, because that's a bigger number than we started with from the sun. 117 units makes it out into the atmosphere, of which 111 units on average are actually trapped by our atmosphere. Trapped by gases we call greenhouse gases, the gases which are going to be absorbing at specific wavelengths. Gases like water vapor, carbon dioxide, etc., are absorbing this radiation in our atmosphere and warming the atmosphere in this process. Without our atmosphere, our temperatures on Earth will be far, far colder than they are today. Of this, about 6 units makes it out to space, straight through, not collected by greenhouse gases. But now the atmosphere itself is getting warm, and it has a temperature, therefore it's going to radiate energy both up and down. So the atmosphere radiates some 64 units back out to space and 96 units down to the ground. Now, if you go through the numbers here, we started up 19, and then we've added some, we've subtracted some along the way here. If you do the math, you'll see that winds up being 0. The Earth energy balance is 0, and therefore, without a change in the amount of energy, the atmospheric temperature would stay the same. Likewise, on the ground, we started with 51, we start subtracting some here, adding some, we wind up averaging out as 0. So the balance we have on Earth has been maintained for many, many years, The challenge when we think about greenhouse gases, if you increase the greenhouse gases, you're increasing the blanket here, you're increasing the amount of this energy which is going to be absorbed by the atmosphere, re-radiated back down to the ground. That potentially can make our ground temperatures and ocean temperatures rise as a result of increasing greenhouse gases. Now we bring this all up because the creation of a hurricane takes advantage in particular of this evaporation latent heat channel here. So here we have the entire Earth atmosphere energy balance. And if you go through the numbers along the bottom and each layer, you see they all wind up at zero. That is, there is no extra energy laying around here anywhere. If we had a surplus of energy at the surface, temperatures would rise. If we had a deficit at the surface, temperatures would lower. And these are global averages over all time. So you can imagine, like at nighttime, this column goes away. There is no solar energy at night, and therefore this channeling over here becomes the most important part of this, which is important when thinking about the potential for global warming, because the greatest impact from any global warming is likely to happen when the sun's not shining, and that's going to be your Arctic regions and nighttime. And it's this layer in here then which dominates the heating of the ground during those conditions. For hurricanes, it's this portion, the evaporation latent heat exchange, which is most important in driving tropical storms and hurricanes, and different from the kinds of storms we get normally in the Midwest. Latent heat is a result of phase changes in water, and we have three phases. Obviously, water vapor is a gas, water the liquid, and ice the solid. When you exchange one for another, if, for example, we're going to do evaporation, it takes energy, and it takes exactly 600 calories to evaporate a gram of water. And so you take the water, you evaporate it maybe in the Caribbean, you move the water then as water vapor up to New York or Midwest, and a cloud forms there, you get the energy back when condensation occurs. And you get back 600 calories for a gram of water that's condensed at that spot. So this is a great way to move energy around in our atmosphere. Evaporate the water in the tropics, move it out of the tropics into temperate regions, and have clouds form as a way to exchange the excess energy from the tropics. We can go other routes here as well through sublimation and freezing. I'm not going to worry about those today. The main feature we have in hurricanes is going to be the exchange here between liquid water and water vapor. Now on Earth, that graph that I showed a moment ago with the energy coming from the sun is the global average. But your mileage will vary depending on where you are on Earth, how much sunlight you get, far more in the tropics than in the polar regions. Means that in the tropics, they have an excess amount of energy. That is, they're gaining more from the sun than they can exchange back into the atmosphere, exchange back out to space. So in this, you see that the orange areas represent where the excess amount of energy is. And this varies over with season, going south in our wintertime, north in our summertime, back and forth the excess amounts of energy. And if you have excess energy, that is, if your net balance is greater than zero, your temperatures must go up. If there's a deficit, your temperatures must go down. And in order for the temperatures to remain constant, there has to be some other exchange going on that we didn't talk about, and that's horizontal. That the energy, excess energy from the tropics, can be exchanged to the north and the south. So we have a surplus in general in the tropics. That excess energy then is transported north and south to areas of deficit, and in that way, this is going to exchange energy in the horizontal. Now, that energy exchange in the horizontal comes in a number of ways. One of them is the movement of sensible heat. Basically, the warm air from the south here in Michigan brings with it often warmer air. That's the exchange of sensible heat. Second, ocean currents carry a great deal of this energy from the tropics up into the more temperate and polar regions. And lastly, latent heat, that evaporation of water in the tropics carried out into the more temperate areas where the clouds form is a great way also to exchange energy away from the tropics. And this is the driving mechanism which helps us understand why hurricanes. Hurricanes are a superb way of moving a lot of energy out of the tropics in a hurry. And when there's excess energy in the tropics, it will lead then to, can lead, let's say, to hurricane formation under the right conditions. As an example for how the energy is removed from the tropics, here is an image of every hurricane, typhoon, and cyclone since 1950. And you can see from the path of each track that they're systematically moving energy out of the tropics. Now, I challenge you to look at this image and think what part of this image does not make sense to you. Because this is precisely the kind of question that leads to discussion in my classroom. I invite you now to come and view that class and see how we use these images in the classroom to talk about hurricane formation.